Hello, AP Calc students. Welcome to the last topic before our test. It's a little thing called linear approximation, which is a way to use tangent lines to approximate curves, and there's some assumptions built into it, but we'll talk about all that moving forward here. But basically it's this. So if a function is what they call well-behaved, which I know is a weird way to talk about a function and not like a human being, we can approximate the value of the curve near a certain point with a tangent line. And it makes it easier to approximate than using the actual function. But basically everything you need to know to do this, you already know how to do. But the idea is like, if I can figure out the equation of this tangent line, then for values of, so let's say this value right here is x equals a. You can see the coordinate, x coordinate is a. If I choose x coordinates that are near a, like this is a plus a little bit, it doesn't matter what the little bit is called. Maybe I'll call it dx for like a small change in x. Then like this is the value of a, this is the value of that curve of the line at a, and this is the value of the curve at a, and these y values are close together. The y's are close together. And so like the line is a decent approximation for the curve when you're pretty close to a. As you get farther away from a, like if you're way over here, this is the value of y on the line, and this is the value of y on the curve, and those aren't so close together. But if you stay pretty close to here, and then the line is going to be pretty close to the curve, and so it's going to be a pretty good approximation. And this is why it's important that the functions are what they call well-behaved. It means like it's not like, it doesn't look like this. Like if that was the case and you chose this point, then like as the tangent lines are like not, like this is like never really that close. So like you want like a nice smooth curve. That's when we say well-behaved. And the ones that we give you are going to be well-behaved. So you're not going to worry too much about it. But the formula for this, if you want to call it that, is that the y value or f of x value, the approximation of this, the approximation of f of x is f of, so we can call it x naught, x0, plus f prime at x0 times x minus x0. And what this basically is just a rewriting of, this is y minus y1 equals m times x minus x1. And like basically the y corresponds to f of x, and y1, which we know is like a number, corresponds to this, and m is the same as the derivative, and x1 is the same as x0, and x is just x. So like this is just like if you add the y1 to the other side, you get this, plus this is the derivative times x minus x1, x minus x0. So just like x naught is the point, x0 is the point that you plug in. So, but you'll see how this works in just a minute. I'm going to kind of do it like this probably, and then we can add the number over. You often want to solve for y in these, which is why this is written this way. So let me give you an example. So this says compute the linearization. That's what this is called. We're going to linearize. We're going to turn these things from this curvy thing into a linear thing. So you need a point and a slope. Basically, we're going to write the tangent line to this curve at this point, which you guys already know how to do. So first, let's get the point. F of x is x to the fourth. So f of 1, because they're asking about it, x equals 1, is 1 to the fourth, which is just 1. Which tells me that the point is going to be x is 1 and y is 1, right? X is 1, y is 1. So that's the point. Now I got to find the slope, which is f prime of x, which in this case is 4x cubed. And f prime at 1 is 4 times 1 cubed, which is 4. So m, so to speak, the slope is 4. And so now we can write the curve. We would write it like this: y minus y1, y minus 1 equals m, which is 4 times x minus 1. I just plugged in x1, y1, and the slope m. And then the way we usually write these is we'll add the 1 to both sides. So y equals 1 plus 4 times x minus 1. And this is the linearization. That's what we would call this. This is the linearization. And to kind of refer back to the formula, it's like this is f of x0 plus, this is the derivative at that point x0 times x minus x0. This is the formula I gave you, and it's like f of x is y, f of x0 is the function evaluated at the point, in this case it was x equals 1, plus the derivative evaluated at that point, that was 4, times x minus, and then the x1. So like all these things, this is kind of one formula, but for linearization, we normally write it like this because we usually solve for y. Get the y by itself. It's not quite mx plus b form. You could certainly write it that way, but it works like just like this. And then we use this to approximate f of 1.2. So we're going to use this same linearization, the one that we just found. Y equals 1 plus 4 times x minus 1. And we're going to approximate it at 1.2 by just plugging in 1.2 and for the x. Remember, this is an x value. So y of 1.2 is approximately 1 plus 4 times 1.2 minus 1. 1.2 minus 1 is 0.2. So it's 1 plus 4 times 0.2. 4 times 0.2 is 0.8, so it's about 1.8. I would like you guys to write approximately here in the first step. You can write equals after that, but like this is not really y of 1.2. Y of 1.2, well, we can check. Y of 1.2 is equal to 1.2 to the fourth. 1.2 to the fourth is that's 12 to the fourth with the decimal point in a different spot. So that's something you could calculate fairly easily. It is 2.0736. And we said it was 1.8. 2.0736. So I don't know. Is that a good approximation? It's not super, but it's decent. If you think about it, like the steeper the slope is, probably the less accurate this is going to be the farther away you get because the curve is changing a lot. So with a slope like 4, that tells you this is not going to be a great approximation, but it's pretty good. So that's how we do this. You compute the linearization by like writing the equation of the tangent line at the point they give you. Then you just plug in whatever x they're asking you for. That's how you do the approximation. So this one says, sometimes we have to be smart to use it. Luckily, you guys are pretty smart. So it's like approximate f of 25. Well, it might be hard to do that without, this time it didn't, like here, it told us what x to use instead of x equals 1. You're like, well, what x am I going to use to approximate the cube root of x? And you're like, well, let's choose, remember, the closer like we set up here, the closer this thing is to the point that we choose it at, the better the approximation is. So what would be a reasonable choice of an x for the cube root of x? Well, I'd like one that's a perfect cube. That would be good. And the closest perfect cube to 25 is 27. I'm going to choose that because it's going to make my numbers easy. So I'm going to approximate this. I'm going to write the linearization of y equals the cube root of x at x equals 27 because that's close to the number I'm looking for. So f of x is the cube root of x. F of 27, I chose 27 because it was close to 25, is the cube root of 27, which is equal to 3. So my point is x is 27 and y is 3. So that's like the point I'm going to use when I write the linearization. And now f prime of x, well, this is really x to the 1/3. So it's 1/3 x to the negative 2/3. And since I'm going to want to plug a 27 into this, I'm going to have to rewrite this with a radical so I can actually evaluate it. So remember, the negative exponent means you do 1 over the thing to the positive exponent. So that's 20, so it's x to the 2/3 on the bottom. And that's really 1/3 times 1 over, and remember, this is like the index of the radical and the 2 is the power. So it's the cube root of x squared. And now I can plug a number in here and actually evaluate it. So f prime of 27 is 1/3 times 1 over the cube root of 27 squared. And the cube root of 27 is 3, and 3 squared is 9. So this is 1 over 3 times 1 over 9, which is 1/27. So this is my slope. This is my m. So my approximation is going to look like y minus 3 equals 1/27 times x minus 27. Let's see, y minus y1 equals m times x minus x1. That looks good. 3 squared is 9. Yeah, we're good. And then, like I said, we'll write it like I add the 3 to both sides. So I get 3 plus 1/27 x times x minus 27. And now I just plug in the number that they asked. This is now my linearization. And now I'm going to say, I wrote y of 25 before. You could write f of 25. This just like reminds me that I'm plugging in 25 for x. Oop, screwed that up. Remember, this is not an equal sign anymore. This is an approximated sign. It's approximately 3 plus 1/27 times, now I plug in 25 for x, 25 minus 27, which is 3 plus 1/27 times -2. So it's 3 minus 2/27. See, 3 is 81/27. So this is 79/27. And that's my approximation. So just for a giggle, let's take a look at what 79 over 27 is equal to. 79 over 27 is 2.926, pretty closely. So this is about 2.9. I'm just going to give us a feel for how good this is. 2.926. And since I have a calculator, I can just tell you that the cube root of 25 is 2.924. So it's actually a really good approximation. Like the first time I see a difference is in the thousandths place. You remember this one, the approximation wasn't great because the slope was pretty big, 4. But in this one, the slope is 1/27, which is much, much smaller. And so the approximation is much, much better. So when we do approximations, we're going to do this. We're going to basically write a tangent, the equation of a tangent line, which is what the linearization is. Then we just plug in the x that they're asking us to approximate it at. So there's a couple more examples here in the notes, and I'll do those in the next video.